Alright, here we have a shark or something somebody caught. Fine. They're hanging it up for whatever reason they do this. And here are some facts about the device that's hanging it up. It's 5 meters tall, 2 meters over to where the shark's hanging. The problem with it, though, is that it's in, I don't know, wet dirt or something. And so it's pretty free to rotate about the ground right there. So it can rotate. That's why they tied it up with this rope here. And we want to find the tension in that rope. Okay. So this is going to be a torque problem. I don't know how obvious that is, but if the rope wasn't there and the ground was, really wet, then the whole thing would just teeter over toward the direction of the shark and kaboom, fall that way, right? So the tension in the rope being there is what's preventing that from happening. And since without the rope it would rotate, well, that's sort of a hint that it's a torque problem. So, I guess I'll redraw this in a free body diagram form better. So this is my shape. I've got the weight of the shark right here, mg. We're going to ignore the mass of the apparatus itself. It's probably insignificant compared to the shark. And we have a tension coming off here that we're looking for, and we know this angle. Okay. We also know these distances. I'll call them, I'm going to use R for distance because, I don't know, that happens in torque for some reason. I'll call that R1, and I'll call this one R2. This is my pivot point at the ground, and I'm going to refer to clockwise rotations, counterclockwise rotations, as positive. So here's my free body diagram. Yes. So in order for the tension to do its job, for this thing to not fall over, the sum of the torques has to equal 0, right? And that will be equal to the torque due to the tension minus the torque due to the gravity. So if you look, if the torque due to the force of gravity on its own would cause this thing to rotate in the negative direction, whereas the tension would cause it to rotate in the positive direction. So that explains the signs. Now, keep in mind that the definition of torque, the torque due to a force, is the force times the distance to the pivot point times the sine of the angle between the force and the distance. So let's apply that to these torques. All right, so just filling in here, 0 equals, so the torque due to the tension, well, that will be the force of tension itself times the distance from where the tension is acting to the pivot point, which I called R2, and we know that, times the sine of the angle between tension and R2. So the angle between tension and R2 is this theta 30 degrees. Okay, now that's going to be, move that down a little bit, minus the torque due to gravity. Now, the torque due to gravity, well, the distance straight from where it's acting to the pivot point, that's this sort of hypotenuse right along here, and we'd have to find that and then also find the angle between that hypotenuse and the gravity. Sounds like a pain. So let me let you in on a little trick for solving these torque problems. We are actually free to move a force along its line of action, by which I mean I can move it straight along its arrow or straight back its arrow. I cannot move it from side to side. I'm not allowed to do that because that would change the distance that it's to the pivot point, basically. Now this, well, it seems to do that, but this is actually valid. I can move it to anywhere I want. So how about I move it straight down to here such that this distance is still R1, but now I have 90 degrees. Look at that. So just a quick proof that I'm allowed to do what I say I'm doing, or at least an intuitive discussion. Let's say we have a weird looking bolt and we are trying to turn it with a wrench like so. There's my wrench. So let's say I'm pushing on it like this with this force F. There. So, I'm trying to push my wrench. But wouldn't I achieve the exact same results of that push if I was to, say, just somehow attach a rope and pull with that force F? It would be exactly the same. It doesn't matter if you're pushing or pulling. We're allowed to move forces straight along their line. We are not allowed to move them from side to side because that would change the torque. But this actually is a valid trick. All right, so get out of here, wrench. So what I've done is moved mg to down here, which is fine. So now if you look at it, the angle between mg and r1 is 90. So the torque due to gravity is the force, mg, times the distance to the pivot point, which is r1, times the sine of 90. Okay, and so I know r2, I know theta, I know m, I know r1. So t is our only unknown, and we can solve for that. T equals mgr1. Sine of 90 is just 1, right? Divided by r2 sine of the theta. All right, so you can plug the numbers in there and we'll figure out what the tension is in this rope. So actually a pretty quick problem.